For this problem, we have the following given information, which we are now going to summarize. So given here is the balanced chemical equation. Methane reacting with carbon dioxide in a reversible reaction to form two molecules of carbon monoxide and two molecules of hydrogen. For this particular reaction, its equilibrium constant K sub B is given to be 3.548 times 10 to the power of 6 at a temperature of 1200 Kelvin. We also know initially we have 10 atmospheres of methane gas loaded into our reaction vessel, along with 15 atmospheres of carbon dioxide. So with all of this given information, we are now tasked to be able to compute what is the pressure of methane remaining at equilibrium. So to be able to solve this one, we have to first try to look at the value of our K sub B. Since our K sub B, we notice is a very large value. It's 10 to the power of 6. We recall from our lessons previously that we have the following steps to guide us in solving. So the first thing we need to do is to first compute what will be the partial pressure of our carbon monoxide product and the hydrogen along with the excess reactant, assuming that this particular reaction has gone into completion. Now for this one, we have the following. If you look carefully at our given pressures, methane is 10 atmospheres, carbon dioxide initially at 15 atmospheres. For all of the methane to be able to be used up as the limiting reactant, it would actually require 10 atmospheres of carbon dioxide to react with it. So only 10 atmospheres of carbon dioxide is needed, but we have here an excessive amount, which is 15 atmospheres. So we then conclude that definitely our methane is the limiting reactant. And since our reaction has been assumed to go into completion, the partial pressure of the methane will have become 0. As for the carbon dioxide, once the reaction has gone completely to form the reactants from the limiting reactants, to form the products from the limiting reactant, we're left with the following pressure of carbon dioxide, which is then computed as follows. So 10 atmospheres of of methane, which is our limiting reactant, and basing on our stoichiometry coefficients from the balanced chemical equation, we have every mole of carbon dioxide should react with 1 mole of methane. Plugging all of that into the calculator gives us an initial pressure an initial partial pressure of carbon dioxide, which is 5 atmospheres. Now for our products, carbon monoxide and our hydrogen, looking again at our balanced chemical equation right here, we are now able to compute the following. So initially, both of these have an initial partial pressure of 0, but as our methane is being consumed, it is being converted into carbon monoxide and also our hydrogen, which it turns out is equal to one another since the coefficients of carbon monoxide and the hydrogen are the same, so that we have its initial partial pressure, which is the following. So that is equal to 20 atmospheres. Now, having computed the partial pressures of the products and the excess reactant, we now set up our IC table. So for this one, we copy the equation that we have earlier. So we have methane plus carbon dioxide reacting with one another to be able to form two molecules of carbon monoxide and two molecules of hydrogen gas. The initial partial pressures of all of these in ATM are as follows. So we have 0, 5, and 20 each for both products. Now to express this initial partial pressures as activities, we simply divide all of these given partial pressures by 20 so that we are left with the following. 0 divided by 20 should still give us 0. 5 divided by 20 gives us 0.25. And of course, 20 divided by 20 gives us 1.000. Now, as this particular reaction tries to establish its equilibrium, some of the products will be used up to be able to reform the methane and carbon dioxide. So the amount of carbon monoxide will decrease. Same with the amount of our hydrogen to be able to form some methane and some carbon dioxide. The quantities of these reactants that are reformed are unknown, so we signify them as X. So that at equilibrium, we simply sum up the initial activity of each chemical species with a change in its activity to give us the following. So methane has an activity of X, carbon dioxide has an equilibrium activity of 0.25 plus X, and our two products each have the same equilibrium activity of 1 minus 2X. Now with our ice table already set up, we are now ready to write our K sub P expression for the following reaction. So that's step number 3 in our guide. And we now do that to give us the following. Our K sub P is then expressed in terms of the equilibrium activities as the activity of hydrogen at equilibrium squared times the activity of carbon monoxide at equilibrium also squared divided by the equilibrium activity of methane multiplied by the equilibrium activity of carbon dioxide. Now, according to step 4, we now substitute the equilibrium concentrations from the ice table into the K sub P. And that's what we do now. Our K sub P is given to us as equal to the following. So we substitute this value right here. So K sub P is equal to 3.548 times 10 to the power of 6. For the hydrogen and carbon monoxide, their activities are taken to be equal to 1 minus 2x, and that is raised to the power of 2. For methane, its equilibrium activity is given as x, and for carbon dioxide, its equilibrium activity is 0.25 plus x. Now to simplify our problem solving, since we already know that our K sub P value is extremely large, we can just use our small x approximation. So we have to assume in here, for the sake of simplicity, that the following is true. Namely, that the amount of products that are used up is so small that basically the equilibrium activity of our products is just about the same as their initial activities. Doing so simplifies our computation tremendously. So we're left with the following. So the value of K sub P, we copy that one. And that should be approximately equal to our numerator, which simplifies to become 1 squared times 1 squared all over x remains as it is. And as for the other term on the denominator, so since x is a very small value, we assume that the sum 0.25 plus x is just about equal to 0.25. So simplifying this expression and then solving for x, we are now going to get the following. So x should then be approximately equal to 1 divided by 0.25 times 3.548 times 10 to the power of 6. So plugging that into the calculator now gives us an approximate value of our x, which is then found to be 1.127 times 10 to the power of negative 6. Now, since we've obtained the value of x using an approximation, this value is worthless if we do not check the validity of the assumption that we made. So to check the validity, we return to our assumption for the small x approximation. So that is equal to, that is now going to be the taking of the percent error. That's 2 times the value of x divided by 1 times 100%. If the value of this percent error is greater than 5%, then we know that the approximation that we have made is not a valid one to do, and so we have to solve for the x using a different method. But we're lucky in this regard, since using our calculator, we find the percent error here to be equal to 2.255 times 10 to the power of negative 4%. A very small percent error indeed. So this verifies to us that the assumption we have made is valid. So since the value of x is going to be very close to the actual value, we can now compute for the partial pressure of methane at equilibrium using the value of x that we have obtained here. So the partial pressure of methane at equilibrium is going to be about equal to its equilibrium activity times 20 atmospheres. Now going way back into our ice table, the equilibrium activity of our methane is equal to x. So substituting it here, the equilibrium activity is x times 20 atmospheres. And substituting the value that we have computed earlier, the partial pressure should then be equal to the following. So the partial pressure of methane should be approximately equal to 2.25 times 10 to the power of negative 5 atmospheres. But since this very small pressure is not a very practical means of measuring our pressure, we can just simply make a conversion for this one, remembering that an atmosphere of pressure is equal to 101,325 pascals. We can also express our answer in terms of Pascal to be equal to 2.28 pascals. And that is how much methane is left in our reaction vessel at equilibrium.